The paper titled Synchronization of Velocity and Position using PI PID and DOB controllers is presented by myself, Amram Dedovic, and it is presented for IEEE International Conference on Automatic Control Intelligent Systems, and the co-authors for the given paper are Sheila Jakmic and Nadia Vitishkic. Okay, the outline, we'll be talking about the abstract information, brief mathematical derivation, simulation results, experimental results, conclusion, and references. Now, a small intro for the brief mathematical derivation, simulation results, and experimental results. Now, they will be giving you giving sort of a notion of aerodynamics and how we go around, how do we make control variables, and how are we eliminating disturbance. Now, in simulation results and experimental results, we'll be providing you the differences between disturbance observer and PID or PI controllers for the various references. The references can either be constant values that are they are constant, but we will be changing constant values in a cascaded manner such that you will see various constant values, and then you can compare which controller is better, disturbance observer or PID for the given application. Okay, and lastly we'll be concluding and providing you with the references. The general information, what we have come up or what we have discovered in the given paper is that disturbance observer controllers, they are outperforming PID controllers because they have fast response and they have minor ripple. And the good thing about disturbance observers is when you design them in a proper manner, either you can use it, it's not necessarily too difficult to design them because you can do it with the first second order filters. And the good thing, as mentioned previously, is that they are very easy to tune. What does that imply? Implies that you don't have many gains to play around with. On the other hand, if you are tuning PID or PI controllers, you have a lot of gains to play around with. You have integral gain, you have derivative, the proportional one, and if you're not tuning them in a precise manner, you will reach oscillations and it will be very, very difficult to tune. So these are the downsides of the PID controllers in comparison to the disturbance observer. And we'll be providing you with the graphs so we will have the whole picture of what is going on. Okay. Now, the brief mathematical derivation, the system equation is well-known derivation for the DC motor. This is well-known mechanical and electrical derivation. So we will assume that you already understand what is going on here because obviously, well, actually, this is very, very simple. You have the torques and you have the electrical part for the voltage with the back EMF. This is already real standard stuff. Now, what we will be talking about here and the way we want to define our synchronization is the following. Now, here we have the following. Imagine we have the first error that is comprised of two velocities. We have velocity 1 and velocity 2. These are angular velocities, obviously. Now, if we take the first one as a positive, the other one as negative, so if we subtract the two, we can make the error go to 0, right? And we know that if they are equivalent, if the error goes to 0, V1 has to be equal to V2, right? And in the second case, okay, we assume that, okay, we have them, we don't assume, but let's say we have that V1 and V2 are going to 0. How can we control them with a specific reference? Now we know that they have to be equivalent since they are equivalent by the first error equation. Well, if we add -2 reference value, then we know that if we track, if they are equivalent, if V1 is equal to V2, then the reference value will be tracked because they have the same values. So if we add them up and -2 reference, they should provide the error to go to 0. So if we take a derivative, which we actually did, and we have the control part and also the disturbance, and now if we can make any control part, either the estimated disturbance observer, which is the disturbance observer, or we can estimate obviously, or we can use PID controllers or PI controller depending on dynamics in the omega case, or for the angular velocity we can use PI controllers, but for the theta or for the position we have to use PID controllers because the poles have to be on the left side, they have to be stable, and we have the convergence that we are trying to asymptotically reach. Okay. In our case here, first of all, we can use, you see, in the previous equation we mentioned velocity, but the angular velocity obviously. But here we can use thetas or positions, or angles, however you want to look at it. Now, if you take position 1 minus position 2 and you go to the PID controllers in a control loop, it will give you, now obviously if you have to look at it in two different ways. First one is obviously the one that is already presented in terms of the errors, right? And then when they are reached, now through some controller, in this case PID controller, you have control values, and they have to be added because the dynamics or subtracted, and they will be providing you the input currents to go to the plant. And now the input currents in the inner loop, we're not providing that because you can figure that out. Now the inner loop, if they are reaching the values of the inner current, And now the current of the system, obviously, and then afterwards you're reading your thetas, theta 1, theta 2, or angles, and seeing if you are reaching the values that you're trying to reach. In this case, you're trying to reach the physically possible reference value, which is 2 reference values here. But obviously, if you put 1, you know that these are going to be, obviously, the reference value. If you multiply by 2, obviously they are, when they add up, they have to be equivalent to this one, right? Okay, now this is for the PID control, and the only difference is, you can see here, you have PID for the disturbance observer. Instead of I term, the PD has to be used such that the dynamics is stable. Now for the disturbance observer, you can see here the values, the only difference is it is kind of estimating the integral part. And there are some constants you don't need to worry about, but essentially it's the same thing, but instead of the I term, you have the disturbance observer. And it outperforms significantly in real life, in experimental results. They show that it outperforms the PID controllers because the both motors are having fast response and they are synchronized without much ripple. So it is, and the tuning is relatively simple. You see here, and this is the same dynamics, everything is the same. And the inner loop, I reference, they are reaching the I1 and I2, which is the currents of the system, and we're reading it with encoders theta 1 and theta 2. Okay, and we're having that there. Now, with regards to simulation results are interesting because in simulation we are trying to see if the mathematical results are obtainable, and they are obviously obtainable. So in simulation you can put, or you can tune it relatively simplistically because you understand the math and you can do it mathematically, which is actually just proving that the mathematical derivation can work. And you can see here the error graphs. The interesting part to mention here, the green graph is actually V1 and V2, which 2 angular velocity which are synchronized. So you can see they are on top of one another, and also the black are 2 velocities for the disturbance observer. So they are V1, V2. So you're synchronizing 2 motors. Essentially, you have four measurements here for the simulation results. So they're on top of one another, and you can see that they are overlaying each other. So which means that we can tune both controls to work in the same manner for the simulated results. Now, interestingly enough, these are for the reference, and the reference is the constant signal. Now, if we take a reference to be sinusoid, in which it has 0.1 hertz frequency, now we can have that. We have the overshoots a little bit more difficult to tune the PI controllers with respect to the DOB controls, but you can see that both of them, when they reach the steady state, when in transient you have the overshoot, but when they reach steady state they perform almost identically with regards to the DOB results. But we are talking about here, we're trying to understand which one is having fast response, which one is easier to tune. If you have overshoot, some systems is not desirable, and so on and so forth. Is it fast response? How fast? And so on and so forth. So here we see, even in simulation, the PI controller is being outperformed by DOB. Yes, one can argue that we can tune it in a better way. PI controller can perform in a similar way as the disturbance observer, but it requires you a lot more tuning, and obviously which is not desirable in our case. Now, this is for angular velocity simulators, synchronized angular velocity for sign reference with PI and DOB, which is displayed here. And you have to keep in mind that these are, whichever graph is displayed, it's 2 velocities on top of one another, which means that they are synchronized. Okay, same thing here. 2 velocities V1, V2 for the disturbance observer controller and PID controllers. Now the theta has to be PID control. You have to use PID controller because of the dynamics of the system. It's a second order system. Okay? And you can see that we have a fast response for the error dynamics, which is comparison between errors for the PID and DOB for the sign position reference. Obviously, here you see that in simulated results, it is we have a fast response for the disturbance observer, and not only that, both of them are reaching a steady state and they are reaching the sine wave, which is very much desirable. But we cannot, from these kind of simulated results, we cannot immediately conclude which one. We can conclude in one way because of the simulation, but we cannot be 100% sure that the disturbance observer is outperforming PID controller, right? So for that, we have to do some experimental results, which we did utilizing 2 DC motors. Now, 2 DC motors, they have gearbox 43-1. It is displayed in the paper, but the general idea here for the experimental result is to mimic the simulated results in one way. So we were sending this the reference signal, which is constant, and this is synchronization of the constant velocity with PI and DOB the disturbance observer controllers. So we see here that the signal that is constant is actually constant because for this given duration time we're giving the signal, it is constant. So now for the first one we have velocities let's say the disturbance observer V1 and V2, these velocities, they are synchronized, and we have two velocities on top of one another. So you can see that it's kind of, when they're synchronized and they're moving in the same way, you see it as a one graph, but actually there are two velocities for both of them. So actually 4 measurements are displayed here as well. So you see here, what's easy to immediately observe is that the disturbance observer has a fast response, a lot faster convergence in comparison to the PI or PID controllers, in this case PI controller. And you can see that aerodynamics for the disturbance observer, they are only in the transient, there's a high spike, and they are immediately there. They are immediately being synchronized. And even in spiking, they are synchronized, which is interesting. Another thing is, if we use, this is for the velocity that is having the constant reference, okay? Now, synchronization of sine velocity with PI and DOB. Now, in sine wave, it's interesting to mention that we have oscillations. And the oscillations is because of our inability to precisely tune it at 0. So we have some small oscillations. But for the disturbance observer, these oscillations are destroyed, to put it simply. So we have a smooth sine wave that is actually tracked by 2 motors, which are synchronized. They're tracking the blue sine wave. Okay, and although actually the black one, it's representing PI controller, and it is not. If you think about the error synchronization for the velocity PI and DOB, you can see here these small ripples. We have a higher ripple, obviously, in comparison to the disturbance observer, which is very, very minimal. It's almost not observable. It's less than 0.001, which is actually negligible. Okay. Now, the interesting thing to mention here is the synchronization of the constant position with PID and DOB controllers. Now, here is interesting. What we did was we did a cascaded structure. What is that implying? We put the constant values, but in a cascaded manner, such that when you reach a position, because when you reach a position, the encoder is giving you one value, and that's it. The motors are stopping. So we put some different values when it reaches, let's say, 2 revolutions. Then we are switching it to 2 or 3. In this case, it's 3, and then to 3.5 and 4 and whatnot. And that's the kind of a way that we did this experiment. And in experiment, we can obviously see that the disturbance observer, both of them, even in transient, both are synchronized. Here you can see 2 graphs are on top of one another. The disturbance observer for both theta 1, theta 2, they are red in color, and it's almost indistinguishable from one another because they are synchronized even in transient. And also the synchronization, the PID, using PID control, they're synchronized in transient, but you can see a little bit there gap between them. And obviously the transient is faster, the convergence for the disturbance observer is faster. So if you use an error graph, you'll see that both of them will be reaching the steady state, and both of them are reaching the values that we want them to reach. But obviously the disturbance observer in our case is outperforming the PID controller. Okay. And the sign reference is the same thing. The only difference is that there is a minor gap in between following for the PID controller. You can see that in error graph, but essentially at the top of the sine wave, and essentially both of them, they are behaving in a similar manner. But in this case as well, the DOB is having minor ripple, and it is having faster convergence, which here you can see that it's less than 0.0001, which is almost negligible. Okay. Here, okay. Now, to sum things up, we see that the advantages of the disturbance observer are the following. It has a fast response. It's easy to tune, highly precise, and minor ripple. And the disadvantages, one of the major ones is the complex design. Now, with regards to the PID and PI controllers, they are simple to design. Obviously, you have only the gains that you have to worry about, and they have minor ripple. They can have fast response as well, or medium response. We can put it in that way. But the downside of it, the major one, is that it's hard. It's one of the things that is kind of a thing to keep in mind, is that it's hard to tune them, and they are prone to oscillation. And prone to oscillation because if you don't tune them, they will be oscillating. The system is going to oscillate. Okay. In conclusion, we have seen that the DOB outperforms PI and PID controllers. The minor tuning for the DOB is required, but we can see that because of that minor tuning, we have a high precision, and there are almost minor to no oscillations. On the other hand, the PID controller is simple to design. And so if you think about simplicity and complexity of the design, you can choose PID controllers. And obviously, being on the pros and cons of DOB and PID controllers, you can find your right fit for the given application in question. Okay, these are the references that we have utilized for the given research. And that sums it up. Thank you for your attention.